Welcome, my name is András Strausz, and I'll be presenting our work on distributed memory triangle counting and the computation of the local clustering coefficient. So graphs are a very effective way to represent complex systems from the real world. For example, one may analyze cell-to-cell interactions based on the underlying graph that would consist of the proteins that participate in the process and the relationships in between them. Or we can see the power grid of a country as a network, and we may use graph analytical techniques in order to spot vulnerabilities in that. And in this work, we will focus on a core graph analytical metric called the local clustering coefficient, or LCC in short. LCC gives the likelihood that the neighbors of a vertex are themselves connected. Now observe that the possible number of pairs of neighbors in between an edge may exist is directly given by the degree of that vertex. And in case that edge is actually present in the network, it will form a triangle with the edges already incident to the neighbors. That is, triangle counting is the basic primitive for computing the local clustering coefficient. We can visualize the LCC scores of the vertices on this small network, and it finds mainly the applications in link prediction problems such as community detection or link recommendation. So what are the challenges when one wants to compute the LCC scores? First of all, natural graphs are very large, consisting billions of vertices and possibly hundreds of billions of edges. Therefore, single machine solutions are insufficient, both due to their lack in computational as well as in storage capacities. Moreover, natural graphs possess scale-free degree distributions. That is, for example, if we would zoom in into the network, what we would see is that a small subset of vertices will be connected to a large portion of the network. That is, they will have a large degree, whereas most of the other vertices in the network will have only a relatively small degree. And what it leads to is that it will be difficult to achieve an equal distribution, both communicational as well as computational distribution between the processes. So our goal is to compute the LCC scores in a distributed memory manner. And what we could see is that former works all relied on synchronous computation. Either they were following the BSP framework or they were written in a MapReduce fashion. However, the main scalability limitations came from synchronization costs. And to this end, we develop a fully asynchronous algorithm that is based on one-sided communication. So as I noted earlier, triangle counting is fundamental for computing the LCC scores. And one way to formalize it is formalizing it as a frontier intersection problem for which several methods exist to compute it. And what we found in our work is that a hybrid strategy to decide which method to apply at runtime will lead to performance improvements. And last but not least, graph partitioning is a key point of any distributed memory algorithm for LCC computation, and former works all use static vertex delegation schemes that either led to a high imbalance between processes, or it was a costly pre-computational step that once again reduced performance and may result in very large memory overheads. In our work, we observed that our algorithm offers a potential data reuse in the communication pattern that we will exploit using caching. And this cache will represent a subgraph that will consist of vertices that were regularly used in the past and therefore are expected to be useful in the future as well. Moreover, we improve on the caching performance by an application-specific eviction policy. Our results show in general 4 to 12 times faster results for scale-free graphs compared to TriC. That was the 2020 Graph Champion paper for triangle counting. And our best results go up to 100 times speedup over TriC. So next, I would like to go through our algorithm, where we start by distributing the vertices in a one-dimensional manner. That is, we will assign an equal number of vertices to processes and store the local partition using the compressed parts row format. So triangle counting is really the basic primitive for computing the local clustering coefficient. And we will compute it in a edge-centric manner. That is, we will compute the number of edges that lie on a given edge. For example, in this little example, the triangles that lie on the edge between vertices 1 and 2 is the one that is enclosed by vertex 0 and the one that is enclosed by vertex 4. Now observe that these are exactly the common neighbors of those vertices. That is, we can formulate the number of triangles as an intersection problem where the number of triangles is directly given by the number of common neighbors. And in order to compute the intersection of two neighborhood lists, we either can use, for example, among other methods, we can use binary search, where we would issue a sequence of key lookups where keys come from one of the neighborhood arrays and then are searched in the other neighborhood array, or sorted set intersection, where we would traverse both arrays at the same time, comparing the elements and counting the common ones. So what are the trade-offs there? Binary search will be essential in our case because our focus is on scale-free graphs, and many edges will connect vertices that have a high difference in the degree. That is, in case an edge goes between a low degree and a high degree vertex, binary search is very essential because it has a running complexity logarithmic in the size of one of the neighborhood lists. However, it has a random memory access pattern, and therefore it will lead to many cache misses, whereas sorted set intersection traverses the array linearly, and thus it is more cache friendly. In our work, we derive a boundary rule from the computational complexities of this method and find that deciding at runtime which method to use based on this rule will lead to a decrease in running time by up to 8%. Moreover, we develop a shared memory implementation that leads to 2.7 times speedup using 16 threads. So these first 2 points can be quickly translated to an algorithm. In this, processes would compute the LCC scores of the vertices that they own in an edge-based manner. However, we distribute vertices and not edges. Therefore, many edges will cross partitions. And in that case, a process has to attain the neighborhood of a remote vertex. And in order to achieve an asynchronous algorithm, communication has to proceed asynchronously. MPI RMA offers non-blocking communication where the target process, that is the process where we read the data from, is not included in the communication step. Moreover, for hardwares that support RDMA communication, RMA operations are directly mapped to them that will result in a higher throughput and reduced latency. So I would like to focus on two core elements of MPI RMA that are important for our work. The first is the so-called MPI window, in which processes may expose local regions of memory that can be then later read by other processes that also are part of that communication window. And the function to read remote data is the so-called get operation, where one can specify the window in which that process is reading, the target process from which the process will read from, and the offset and the size of the memory region that we are reading. Now, all in all, with MPI RMA, we can reach an abstraction of the graph where every process will have a global view of the graph. And in case an edge goes between two local vertices, it will result in a local memory read, whereas in case the edge crosses partitions, we will use the MPI get read, that is, we will read remote memory. I would like to remind you that our focus is on scale-free graphs, and the degree correlates with the number of accesses. Therefore, high-degree vertices will be regularly accessed by remote processes. We can run a quick experiment to check this, where we will distribute a small social network among two computing nodes and count the number of RMA reads that are shown on the x-axis that are repeated by given times, shown on the y-axis. And what we can see that from the viewpoint of process 1, 50% of the reads are repeated at least 4 times. That is, we can exploit this temporal locality that is offered by the communication pattern in our algorithm by caching RMA reads. For this, we will use CLaMPI, that is a transparent caching layer built on top of MPI RMA and supports variable size reads. As a result, next to the local partition that is stored at every process, we reserve memory for caching. This cache will represent a subgraph stored additionally that will store vertices that have been accessed regularly in the past, and those are expected to be accessed in the future as well. Moreover, we develop an application-specific eviction policy. As the degree correlates with the number of times a vertex will be accessed, we can use this degree centrality score in the cache in order to store probably more valuable entries in the cache. This led to an improvement between 14 and 35% in caching performance. So this is the whole overview of our algorithm. I would like to just focus on 2 experiments from our paper that were run on the Pistine supercomputer on the CSCS cluster that is equipped with Intel 7 processors, 64 gigabytes of memory per node, and are interconnected using the Craze RIS network. So we'll show strong scaling experiments in this case using a synthetic ARMA dataset that will be distributed among from 4 to 64 nodes, and the UK 2005 somewhat larger real-world dataset that we will distribute among 128 to 512 computing nodes. The pink will show our non-cached implementation, that is, those are results without using caching, just relying on the one-dimensional distributional scheme, and that we compare to TriC, that is shown with this light blue color. What we could observe is that our asynchronous implementation shows often better scaling characteristics, especially for graphs with highly skewed degree distributions, such as the graph generated by the ARMA in this case. And in general, we can see significant performance improvement even without caching. In general, 4 to 10 times faster results. That is, eliminating synchronization overheads is really key for computing the LCC scores on distributed memory. Moreover, we show our cached implementation with this dark blue color. And what we could observe that caching performance is influenced by several factors. Possible data reuse depends on the underlying dataset. In case the network has a rather flat degree distribution, data reuse is reduced, and therefore caching will not be as efficient. In this case, this can be observed on the UK 2005 dataset that is opposed to the synthetically generated ARMA dataset has a somewhat flatter degree distribution. Moreover, as we distribute the graph between more and more computing nodes, compulsory misses will increase, once again, decreasing caching performance. All in all, however, caching could significantly improve on running time, and in our experiments, we could see a reduction in running time with up to 73%. That is, we could improve on a static vertex delegation scheme using caching. In our paper next to these strong scaling experiments, We include experiments where we analyze our shared memory performance, our eviction policy that we developed based on the degree centrality scores, how caching performance varies with respect to the size of the reserved memory, as well as a larger set of final strong scaling experiments that you can all find in the paper next to an outlook, where we set a couple of goals for future research, such as using different partitioning schemes for this problem in order to reduce the total communication, as well as using caching in various other graph computations, or developing new application-specific eviction procedures. All that you can find in the paper. So this talk was about our paper, Asynchronous Distributed Memory Triangle Counting and LCC with RMA caching, where we started by describing the local clustering coefficient and its relationship to triangle counting, set the challenges and the goals for our paper, went through our algorithm, and analyzed our results, where we could find that eliminating synchronization overheads is really key, and caching can significantly improve on a static vertex delegation scheme. Thank you for your attention.